In this video lecture, I shall be discussing FTIR spectroscopy. The discussion will include instrumentation, what is Fourier transform, theory and principle of FTIR. FTIR uses infrared light to scan a sample. Infrared light is absorbed and the absorption depends upon the vibration of the bonds of the molecule. There is absorption and transmission of light depending upon the structure of the molecule, and the process involves collection of the IR signal that comes from the sample. Then the signal is digitized by a device that is ADC, analog digital converter. It converts the signal to a spectrum later by using Fourier transform, and the spectrum obtained finally gives an idea about the structure and identity of the sample. The molecules that can be analyzed may be solid, liquid, gas, but the condition is that the molecule must have some polarity or dipole moment, because after absorbing the IR light, the dipole moment changes, and that change finally generates the spectrum. The molecules which have zero dipole moment like oxygen, nitrogen cannot be analyzed by this particular spectroscopic technique. FTIR is a highly sensitive technique. It employs sensitive detectors. It uses improved optical throughput, and it can be used for the identification of unknown samples, assessment of quality of a molecule, then to measure the concentration, that is for quantitative analysis, qualitative analysis, monitoring of the pollutants, formulation of the drugs, quality control of the drugs, and to study the interaction of drugs in pharmaceutical industries, to analyze the chemicals in forensics, in food industry, in medical diagnostics, and several more applications. Now we'll discuss the instrumentation. The instrumentation includes a source of infrared radiation. Infrared radiation can be produced by using a globe, that is a silicon carbide rod, then nonus blower, incandescent wire, mercury arc, and tungsten filament lamp. There are different types of infrared light. According to the range of the infrared light, a source of the radiation is chosen. For example, the mercury arc lamp is used for far infrared region, and tungsten filament is used if there is a requirement for light from near infrared region. Second important component is Michelson interferometer, and it includes some components like the beam splitter, then there is fixed mirror, then there is a movable mirror and a compensator. How it functions we will discuss in other slide. The sample compartment holds the sample. Sample may be solid, liquid or gas. Accordingly, the design of the sample holder varies. Then there is ATR for analyzing the solid and liquid samples without any complex preparation. There are different types of detector like pyroelectric, photoconductive, thermocouple or thermopile, and bolometer. For near infrared region, lead sulfide and photoconductive detectors are used. Then for mid-infrared, thermocouple, thermistor or pyroelectric detectors are used. For far infrared, pneumatic detector, Golay cells or bolometers are used. There is analog to digital converter that converts the analog signal from the detector into a digital data for processing. Computer is with a Fourier transform software. The Fourier transform algorithm converts the interferogram from the time domain to the frequency domain. Then there is data analysis software to process the data and for the displaying the infrared spectrum for interpretation. Fourier transform infrared spectroscopy is an analytical technique. Organic, polymeric and inorganic materials, solid, liquid, gas, every type of material can be analyzed by FTIR. The molecules selectively absorb the specific wavelength and the only condition is that sample should have a dipole moment. So once the sample absorbs the IR light, the dipole moment or the polarity changes. A part of the radiation is absorbed by the sample, a part is transmitted, and the resulting spectrum, it represents the molecular absorption and transmission. The spectrum is unique to the sample. Each sample has a specific spectrum. That is why FTR, it creates the molecular fingerprint of the sample. Beer-Lambert's law is applicable for all the samples except for complex mixtures. FTIR is a vibrational spectroscopy. So, after absorbing the IR light, the atomic bonds vibrate. Vibration at specific frequency aligns with the absorption peaks of the absorption spectrum. There are different ranges of the infrared radiation like near infrared, mid infrared and far infrared. Molecules absorb IR radiation of specific frequencies that corresponds to the vibration of atomic bonds in the molecule. The energy of the radiation results in transition of the molecule from ground vibrational state to excited vibrational state. There are different types of vibrations such as stretching, bending, twisting. Interferometer splits the IR beam into two optical paths, one to the fixed mirror and one to the moving mirror. After reflection from these two mirrors, the beams recombine and create the interferogram by the detector. There are different types of vibrations such as stretching, bending, twisting motion of the bonds. During these vibrations, atoms remain in their bond axis. That does not change. Type of vibration occurs at specific frequency, which depends on the mass of atoms present in the molecule, their arrangement, and the bond strength between different atoms. Vibration of atoms may be of different types. As shown in this figure, there may be symmetric stretching, asymmetric stretching, bending, rocking, deformation, wagging, twisting, out of plane bending, and in plane bending. If two light phase with the same phase interact, the outcome is high intensity radiation. As the phase difference gets wider, intensity gradually decreases. A plot of light intensity versus time for a monochromatic light generates a sine wave. After Fourier transform, it gives a single peak. This is the interferogram of a bichromatic light. After Fourier transform, it generates two peaks. A continuous light source. After FFT, it produces a superposition of many frequencies which are in phase with one another. Fourier transform is used for interpretation of interferogram and the spectral analysis. It is a mathematical algorithm. It converts complex interferogram into a spectrum. Spectrum generated thus is a plot of absorbance or transmittance versus the wave number. Position and intensity of the peaks provide qualitative and quantitative information about the sample. Fourier transform is a mathematical algorithm or mathematical model. By using this, the signal can be transformed between two different domains as shown here, from time domain to frequency domain and also from frequency domain to time domain. So by using this, any periodic wave can be converted to a sum of sine waves that makes it easier to interpret the signal. Here we can see what happens during Fourier transform. In this first graph, the plot is amplitude versus time and it is a sine wave. And after Fourier transform, a single peak is generated. Fourier transform can convert any signal into a series of sinusoidal waves. Here we can see the result of Fourier transform of three sine waves. The three sine waves of different amplitudes, they generate three peaks, and the intensity of the peak, it is controlled by the dipole moment that happens during the vibration upon exposure to IR light. Here we can see the result of different types of interference. There are two types of interference. One is destructive and one is constructive interference. In this image, the trough of the first light wave is perfectly aligned with the trough of the second light wave, and crest of the first light wave is aligned with the crest of the second light wave. So in this case, there is perfect overlapping of the waves and there is constructive interference. It is indicated by high intensity of the light after interference. In this second image, we can see the trough of the first light wave is aligned against the crest of the second light wave. In this case, these two cancel each other. As a result, there is destructive interference and the intensity of the light decreases after interference. Michelson interferometer is made up of two perpendicular mirrors. One is fixed and one is moving, and there is a beam splitter. The beam splitter transmits half of the light and reflects half of the light because of a coating of silver. Both the transmitted and the reflected lights strike the two mirrors. Reflections from both the mirrors recombine at the beam splitter again and pass to the sample. Path difference is the difference between the light path or the optical path that is taken by light to the fixed mirror and the moving mirror. The path difference may be zero if both the mirrors are placed at the same distance from the beam splitter. Any displacement of the moving mirror along its axis makes the light which strikes the mirror to travel longer distance. Again, that distance is returned. So, the path difference now is a value that is measured by the displacement of the moving mirror. The extra distance is optical path difference or OPD, and it is designated by the sign delta. Here let us understand how the interferometer creates interference pattern by the movement of the moving mirror. The IR radiation that comes from the source passes through a collimator that produces parallel beams of light. The light strikes the beam splitter, split into two halves. One is reflected on the fixed mirror, the second is transmitted to the moving mirror. After that, light from the fixed mirror reflects back to the beam splitter. The light from the moving mirror also reflects back to the beam splitter. Both these lights recombine. Depending upon the position of the moving mirror, an interference is created. It may be constructive or destructive. After interference, the light is absorbed by the sample. A part is transmitted also. The transmitted light is received by the detector, and the detector passes the signal to the CPU that Fourier transforms the signal, and finally a spectrum is created. So as the moving mirror changes the position, it continuously alters the path difference. So what is this path difference? Suppose the fixed mirror and the moving mirror are at equal distance from the beam splitter. Then we'll say that the light traveled after reflection and the transmission. It travels through the equal distance, both from the fixed mirror as well as the moving mirror. Now let us consider this second position. So if the light that strikes the moving mirror comes till this point, then it has traveled an extra distance, and again it returns that extra distance. So the light that travels to the second position, it travels longer path. So here the path difference between this beam and this beam is higher, and this path difference is created by the movement of the mirror. And if the light strikes here at the last position as shown in this diagram, it travels longer still, and it returns that much. So here the path difference is still higher. Depending upon the value of the path difference, the interference may be constructive or destructive. If both the mirrors are at same distance from the beam splitter, the path difference is zero and there is constructive interference. And if there is the path difference equals to the wavelength also, there is constructive interference. Theoretically, if the path difference is any integer starting from 0 to n, a whole integer, then there is constructive interference. But if there is the path difference is lambda by 2, free lambda by 2, like this value, then there is destructive interference. So in this way, The movement of mirror creates different types of interference that enters into the sample. And finally we get a spectrum. That is how the interferometer works. Here there is explanation about optical path difference and the theory of interference. Based on the position of the moving mirror, there may be constructive interference and destructive interference. This has been dealt with in detail at some other place. So this is for the information only. This is the schematic diagram of a FTIR. There is a source of laser. The laser light enters through a collimator that produces parallel beams. The IR radiation falls on the beam splitter that splits the light into two components. Then the light reflects back from the stationary mirror and the moving mirror. Interference is created. The light after interference enters into the sample. Then the transmitted light from the sample goes to the detector. The detector records the intensity of the signal. Then there is Fourier transform by the CPU and final image after Fourier transform is recorded. The detector measures the intensity of the combined infrared beams, and the intensity is a function of the moving mirror displacement. Finally, the detector generates an interferogram, or that is raw data. If the interference is constructive, then the detector detects maximum intensity of the radiation or transmittance, and if the interference is destructive, there is minimum intensity transmittance that is recorded by the detector. These figures show how the interferogram, after FFT calculation by the CPU, it is converted to a spectrum of transmittance percentage versus wave number. The procedure is first to get an interferogram without the sample, and this is Fourier transform to get a single channel reference spectrum. After that, the sample is placed in the sample compartment. Another interferogram is generated, that is the interferogram with the sample. It is Fourier transformed to get single channel sample spectrum, and the transmitter spectrum obtained by using these two data is further processed and digitized to get an idea about the sample. Here we can see three spectra. The first is the single channel reference spectrum measured through empty sample compartment. The second is single channel spectrum of the absorbing sample. And the third is the combined result, the transmittance spectrum, that is obtained by combining these two or comparing these two data. This is the infrared spectrum of ethanol. In ethanol, there are different types of bonds. Let us focus on the OH bond. The OH bond absorbs between 3230 to 3550 centimeter inverse in this region. So you can see transmittance is low, that means absorption is high. The OH bond of the acid absorbs at higher wavelength, wave number. So we can infer that it is from an alcohol group. Then there is a trough between 1000 to 1100, that is 1000 to 1100 here, and this shows the presence of CO bond, and the CH bond they absorb in this region, so that after combining this data with other evidence, we can conclude that the sample is ethanol. This image shows the IR spectrum of ethanoic acid. So by interpreting the spectrum, the presence of wedge bond, CO bond, that is carbonyl group, and C single bond O can be ascertained. So based on this, we can know the composition of the sample. Here we can see the infrared spectrum of 2-hydroxypropanoic acid. As per the structure, the spectrum is generated because IR spectroscopy, FTIR spectroscopy, is a type of vibrational spectroscopy. Depending upon the vibration of bonds, the spectrum is generated. So here, by looking at this data, it can be inferred that the sample is 2-hydroxypropanoic acid. Thank you.